Okay, welcome back to the first session of training for Chemistry Olympiad Round 2. Okay, and congratulations on getting round 2. All right, so like I said, we'll try our best to train before round 2 itself and get as much knowledge as possible. Over the next few trainings, it's going to be intense, it's going to be difficult at some parts. So please stay with me and do re-watch the videos if there's anything you're unclear of. So the first training, we'll be going through the models of the atom, line spectra and mass spectrometry. Okay, so first, let's go through the models of the atom. Hopefully, you know that the model of the atom has been changed over many times in history because of new scientific discoveries. Okay, what are these new scientific discoveries that change our thinking, our concept of the atom? We shall see in a short while. All right, so we are going to go in chronological order, starting from the oldest. Now, one of the older models of the atom is basically Thomson's plum pudding model of the atom, where he said that the electron is in a cloud of positive charge. All right. So J.J. Thomson knew that there were positive charges. He knew there were negative electrons. So his thinking was that the electrons are immersed, moving around this spherical cloud of positive charge. Obviously, today we know that's incorrect. Right? This is not entirely correct. Why is it not entirely correct? Because there's no nucleus. We know today the positive protons are in the nucleus. We know that positive charge is because of the proton, right? Next, J.J. Thomson also didn't know the concept of electron shells. The electrons aren't just like whizzing around, they are in fixed defined energy levels called electron shells. Okay? So this was one of the earliest models of the atom. Okay, but nonetheless, J.J. Thomson at least knew that there were electrons and positive charges in an atom. Next, we go on to Rutherford's planetary orbit model. So Rutherford imagined that electrons orbited around a positive nucleus. So you can see that, wow, Rutherford knows about the nucleus. Yeah, he does. Okay, because there were experiments that were performed that allowed scientists to conclude that there was a dense positive nucleus at the center of the atom. All right. Okay, and this is called the gold foil scattering experiment. Okay, so if you have time, please try to read up on this. Okay, it's the gold foil scattering experiment. Next, we have Bohr's model of the atom. Now, this is close to whatever you are doing today, where electrons are in defined energy levels called shells. So the electrons aren't just in orbit, okay? These electrons are always in defined energy levels. Okay, the energy levels are defined, it's fixed. Okay, now, so Bohr's model of the atom has these concentric circular shells. Okay, and he actually gave the shells names, so he didn't call them first shell, second shell like we do today. All right, he actually gave the shells names. So the first shell is called a K shell, the second shell is called the L shell, and so on and so forth. So that was how Bohr called it. So Niels Bohr, that was his name. Okay, Niels Bohr. Now, obviously, this is still not correct today. Okay, there are no subshells in the Bohr's model. There's no orbitals in the Bohr's model of the atom. So of course, the Bohr's model of the atom is not exactly 100% accurate either. Okay. Nonetheless, the Bohr's model of the atom is actually what you have been taught in Sec 3. Okay, it's one of the most reliable basic models of the atom that we usually teach students at the start of their chemistry studies. Okay, so these are the three models that we'll briefly go through. Now, how did Bohr conclude there were fixed energy levels for each electron shell? Of course, there were experiments performed. And the experiments performed involve what we call line spectra. Okay, so what did we actually do? Now, before we get to this equation, let's go through this little diagram here. Okay, so in this diagram, you are basically given some lines and some arrows. So let's try and make sense of it. N equals to 1 means first shell. N equals to 2, second shell. So on and so forth. Right? So N equals to 3, third shell. N equals to 4, fourth shell, and so on. Now, this is hydrogen. Hydrogen only has one electron. You already know that one electron is in the first shell. So why is there second shell, third shell, fourth shell? Well, the shells are always there. It is just that usually the shells are empty. So in hydrogen, the second shell is empty, the third shell is empty, the fourth shell is empty, and so on. But the shells are there, right? So what Bohr did, or what other scientists did as well, they actually provided energy. And when you provide the energy, you can promote or excite the electron in hydrogen atom to a higher energy level or shell. That means what we did was we actually gave the electron energy so that it can jump, promote from the first shell to the second shell, or to the third shell, or to the fourth shell, and so on and so forth. All right. Then what do you measure? Now, when you promote the electron up, it's not stable. It doesn't want to be in the second shell. It doesn't want to be in the third shell. So it will try to relax back, drop back to the first shell. So we measure the energy released when the electron drops back down. This is the key. Okay, so we don't measure the energy needed to promote. We measure the energy released when it drops back down. Now, initially when scientists did this, they thought that, oh, they're just going to get a mess. They're just going to get like a variety of energies released. That means the electron will release a variable amount of energy. But as it turns out, it's not so variable after all. There are definite amounts of energy being released. And so now let's go through these. The first set involves these purple arrows, which I'm now going to write in red color so that it's clearer. Now, the first set of energies involved the electron dropping back to the first shell. That means from wherever they were promoted to, let's drop back down to the first shell. And it's not some random amount of energy. It's all definite, right? That's why you have arrows that represent these definite changes in energy. Okay, now this is called the Lyman series. The Lyman series is a set of energy changes involving the electrons that were promoted dropping back down to the first shell. The second series is the Balmer series, where they drop back to the second shell. Okay, obviously, dropping back to the second shell involves less energy than dropping back to the first shell, right? More energy is released when it drops all the way down to the first shell. Because the first shell has a lower energy level, the first shell is more stable. Okay? Now, obviously, you can have a different series when you drop it to the third shell, to the fourth shell. All right, so these all have a name. Now, after measuring the energy released, how did scientists represent this on a spectrum? As it turns out, the energy release can be related to the frequency of the radiation release. Now, the energy is released in the form of radiation. Specifically, the energy is released in the form of electromagnetic radiation. So there's an equation that links the energy, the amount of energy released, to the frequency of the radiation, which is E is equals to HF, where H is what we call Planck's constant. All right, and Planck's constant has a specific value. It's a constant, so definitely it has a specific value. All right, and the value is 6.62. Okay, actually use 6.63 is better. 6.63 times 10 to the power of negative 34. So it's actually quite a small number. Now, F is the frequency of the electromagnetic radiation. Okay. Next, we know that electromagnetic radiation travels at the same speed. All right. So we are able to represent F frequency as the speed of the electromagnetic radiation over the wavelength. So lambda is the wavelength of the electromagnetic radiation. C is the speed of light, which is 3 times 10 to the power of 8. Okay, so these two equations are equivalent. E equals to HF and E equals to HC over lambda. All right, so how is this beneficial? We just said, right, when it drops down to the shells, there's a fixed amount of energy change. That means every single arrow here is an energy change. That means every single arrow over here has its own unique frequency, its own unique wavelength of radiation. So we can now represent it on a spectrum. And that's why this is called a line spectrum. The line spectrum shows you the wavelengths of the radiation. You don't just have a lot of lines joined together. They are definite fixed lines, right? So you can see that there's lines. So lines represent definite energy levels. So this was how Niels Bohr did conclude that atoms contain electrons, and electrons are in definite energy levels. So this was one of the first pieces of evidence for the presence of electron shells with definite energy levels. Okay, now something to take note of: Lyman series, the one dropped down to the first shell, dropping down to the first shell gives you ultraviolet radiation, whereas the Balmer series dropping down to the second shell gives you visible light. All right, so for Andre and Junwei, I think you're familiar with electromagnetic radiation. Okay, now then scientists went on to do line spectra for other elements. They did the same thing. Basically, they excite the electrons and see them drop back down to the different shells and see what radiation comes out of it, represent their wavelengths on a spectrum. So hydrogen, sodium, helium, neon, mercury. So actually the line spectrum is kind of like a fingerprint for the element, because different elements will end up having different line spectra, which is logical because different elements have different proton numbers. So the attraction for the electrons in the shells will be different. As a result, the energy of every single shell in every single element is also different. The first shell of hydrogen doesn't have the same energy as the first shell of sodium. Okay, that's why it gives rise to different amounts of energy changes as the electrons drop back down and different lines as a result. Okay, now this can be useful as well. Okay, so you can see that, for example, neon, if I just zoom in into neon, neon releases a lot of red color light. The color here represents red color light. So neon, right, when it's heated up, it tends to glow red color. That's why neon is commonly used in advertising lights to make red color lights. Okay, of course, nowadays we don't use neon anymore. You can just use an LED for the same purpose. But in the past, advertising lights used to be made out of neon. Okay, sodium is interesting. Sodium has two lines. Okay, the resolution is not very good, but you can see two lines, and they're both yellow in color. And that's why sodium, when it's heated up, it glows yellow-orange. Because when it's heated up, what you're seeing is the yellow-orange light that's being emitted as the electrons that are being excited drop back down to the shells. Okay? Can? Now, is the Bohr's model 100% correct? Obviously not. We just mentioned just now, right? The Bohr's model doesn't have orbitals, doesn't have subshells. Okay? So now we commonly teach the quantum mechanical model at higher levels. Now, the quantum mechanical model involves something that's quite unique, which is the idea of an electron cloud in an orbital. Okay, so you have learned orbitals before, right? You have learned S, P, D, F orbitals. So what is an orbital? Orbital is a space in which the electron is most likely to be found. They'd be like, what? You mean the electron is not there? Why is it most likely? Isn't it definitely there? And that's where the quantum mechanical model is interesting, because it doesn't view electron as a particle. It views electrons as having wave-like properties. That means electrons are viewed as waves. What we are saying is the orbital is an area, a region, a space in which the electron is most likely going to have a high probability of being there. But we cannot say for sure. Because the electron is not a particle, it has certain wave-like properties. So it may be that the electrons are not within this space. But we can say with a 95% probability or 99% probability is within this space. Okay, next. This leads us to the conclusion. It is impossible to determine the position of an electron with 100% accuracy. Based on what we just said, okay, it is about probability. The electron is most likely in this orbital, 99% probability. But it's impossible to say 100% definitely is there. Okay, now this principle has a name. This principle where it's impossible to predict the electron's position with 100% accuracy, this is called Heisenberg's uncertainty principle. Okay, now as you go on and do more physics, you will learn how to prove this. Okay, but for now, it is important for us to note that the model of the atom has changed. All right, and today we start to think of electrons as being not only a particle, but it has wave-like properties. It behaves like a wave. It can move, and therefore it is impossible to actually predict the position of its electron with 100% accuracy. Okay. Okay. So we have gone through 4 models of the atom, starting from J.J. Thomson's plum pudding model to Rutherford's orbit model, sorry, not orbital, orbit model, then Bohr's model of the atom, and finally the quantum mechanical model, which takes into account orbitals. Okay. Now moving on, we go on to the last part of today, which is mass spectrometry. Now, mass spectrometry sounds like a very complicated name. Okay, now let's try to break it up a little bit. Mass is obvious. Mass is, how heavy something is, the amount of matter inside a substance, right? Spectrometry. Metry means measure. Measure what? Measure mass. Okay, measure mass in this case. So there are other forms of spectrometry, but this one is mass. What is spectral? Now, when we say there's a spectrum, what we mean to say is there are many different values. So when we say spectrometry, what we mean is we don't expect to see only one value. Spectral means different values, right? So for example, we like to say there's a spectrum of personalities in society. There are different personalities. So in this case, there are different masses. Okay, so how do we achieve this? Okay, so the idea is number one, we actually give a substance, a molecule. So for example, we can give carbon dioxide molecule energy. When you actually give it energy, the bonds can break. The covalent bonds in CO2 can break. That will fragment the molecule. Fragment means the bonds in the molecule are broken. Okay? Next, after doing that, we need to ionize the substance. And usually for mass spectrometry, the machine, the spectrometer, the machine is programmed to give it energy to ionize it to a 1+ charge. Okay, why is this important? Okay, you need to give it the fragment a charge so that it can be accelerated through an electric field, then pass through a magnetic field. So magnetic fields would deflect charged particles. Okay, so for Andre and Junwei, this is similar to how a current containing wire is deflected in the magnetic field. The reason why the wire moves in the magnetic field is because there's current flowing through the wire. So similarly, the ions are moving. Ions moving is like current, right? So charged particles moving in the magnetic field are deflected. The formula is as such. Okay, so please bear with me as I go through the math. Now, the magnetic field is perpendicular to the direction of movement of the ions. Perpendicular is the keyword. Perpendicular means the angle is 90. Okay, so we need this. So the equation is F is equal to BQV sine theta. So let's break this down. F is the magnetic force acting on the ion. B is magnetic field strength. Okay. Q is the charge on the ion. V is the speed of the ion. Okay, finally, theta is an angle. But we already know the angle is 90 degrees, right? The magnetic field is perpendicular to the direction of movement of the ion. So if theta is 90, sine 90 degrees is 1. Hence, you can simplify the equation to F is equal to BQV. Okay, because sine theta is 1. Next, it's deflected in a curved pattern. When something is deflected in a curved pattern, it's a circular motion. So the equation for the motion of a particle in a circle is F is equal to mv squared over r. Okay, again, m is mass, v is speed, r is the radius of the circle that it takes. Okay, so we can equate both forces. So we equate the F together. So BQV equals to mv squared over r. We make r the subject. Okay, we want to find the radius of the deflected path. So r is equal to mv squared over bqv, so that you simplify it with mv over bq. Okay, but that's not it. So now we consider what's r. If the radius is small radius equals more deflection, That means it swerves more, It's like a car that swerves a lot more. It's deflected more. The radius of the path is small. However, if the radius of the path is large, there's less deflection. So this is like a car that's deflecting less, that curves less, then the radius is larger. So we can see if the deflection is larger, the radius is smaller. So it's inverse proportion here. So we can express the deflection as 1 over r. So with that, 1 over r, you flip the fraction around, is bq over mv. So the deflection is proportional to the charge to mass ratio. Okay, now this is the theory behind mass spectrometry. Okay, so these equations show you that, oh, by measuring the deflection in a magnetic field, I can relate it to the charge to mass ratio. All right. Now, for chemistry, we are not so interested in the equations like these usually. What we are interested is the pattern that you get at the end of the mass spectrometry. So typically, the machine, the mass spectrometer, will read out everything and give you something like that. Okay, so this is CO2. CO2 is drawn like that, right? So when you give it energy, the bond will break. So the bond can break in many ways. Okay, maybe this bond breaks. When this bond breaks, you get O plus and CO plus. This might sound like totally unfamiliar to you. Wow, what's O plus? But remember, the machine is programmed in a way to give it a 1 plus charge. Okay, so you will have O plus and CO plus. Now, O plus has a mass of 16. Oxygen has a mass of 16, right? CO plus is 12 plus 16, so it's mass 28. Okay? Can? And of course, not forgetting, if there's no fragmentation, the mass is 44. So, 44 is when there's no fragmentation. The molecule didn't break up. Now, this is called the molecular ion. The molecular ion represents the molecule that didn't break up. So the mass is 44. Also, that's how we know it's CO2, because mass 44 is most likely CO2, right? Next, these ions here represent the fragments. These are the fragments. So as I said just now, it could have broken in a way to give you CO plus and O plus. Do you also see a C plus? How do you get C plus? You get C plus when both covalent bonds have been broken. Okay. Now it's CO2. All right. If you go to something more complicated, dodecane. Dodecane is an alkane with 12 carbon atoms. So C12H26. Now C12H26 can be drawn like this. You have a lot more lines. Immediately you pay attention to the right-hand side first. The right-hand side is the biggest, which is the molecular ion. Do you realize the mass is 170? So based on the mass of the molecular ion, I know that, oh, the MR of this molecule is 170. So I can go and look in the dictionary of compounds, which molecule has an MR of 170? Oh, dodecane. Okay, so the molecular ion is the most useful. Now, the next important thing is the ion that is in the highest proportion. The ion that is in the highest proportion is called the base ion. It's in the greatest abundance. Now, the base ion also gives you an important info, because this tells you the most common fragment. So the most common fragment has a mass of 57. Okay, so we're gonna look, oh, what's 57? Let's think through. Oh, 57 could be, in this case, C4H9 plus. Okay, now I've listed down the mass of common fragments below. Okay, do we actually memorize this? To some extent, yes. So in university, we memorize some of these. So for example, I do memorize 29. I do memorize 15. I tried to memorize 77 as well. All right. But essentially, these are some of the common fragments. Now, when we are lost, most of the time, actually, we just do a quick search. There's a database of mass spectrum of different compounds. So we just do a quick search up. then it's able to tell us, oh, this is this compound, that is most likely that compound, right? So the mass spectrum gives us some information about the mass of a molecule. It gives us some information about what bonds that might be, all right, in a molecule. Having said that, the mass spectrum on its own is not very, very useful because there could be many possibilities. How do you get C4H9 plus? There could be many, many possibilities. All right, Ken? So the mass spectrum is just a quick introduction as to how we can begin to understand the structure of unknown molecules through fragmentation and ionization. Now, before we go, you will realize that there are some interesting mass spectrum. This is one of them, all right? And I'm sure you've seen this before. This is the mass spectrum of, say, Cl2, chlorine, right? For chlorine-containing substances, you will commonly see this mass spectrum. And you notice that this is because of isotopes of chlorine. And you will see that the height of the peak is about 3:1. That means the height of chlorine-35 is about, okay, it's about 3 times higher than the peak due to chlorine-37. And that's why the AR of chlorine is 3:1 means 75 is 25, right? 75% times 35 plus 25% times 37. So it's 35.5. Now we go on to bromine. Now bromine has a similar situation. Bromine has 2 isotopes. But now you see, oh, the isotopes of bromine, the peak in the mass spectrum is not 3:1. In fact, it looks like the same, right? It's like 1:1, right? And indeed, for bromine, the 2 isotopes are present in the 1:1 ratio, meaning the AR of bromine is 50-50. 50% 79 plus 50% 81. And that's why if you read the periodic table, the AR of bromine is given as 80 because it contains 2 isotopes, bromine 79 and bromine 81 in a 1:1 proportion. So when you take the average of the 2 isotopes, it's exactly 80. All right, so if you go to the periodic table now, you search, okay, the AR of bromine is 80. And that's because it has 2 isotopes in an equal proportion. Okay, so hopefully it also shows you that mass spectrometry is important for us to actually work out isotopes, work out the relative abundance of every isotope based on the height of the peak. Finally, based on the height of the peaks, we can work out the AR of that element. So that's what mass spectrometry is also very useful for. Okay, and that actually brings us to the end of today's training. Okay, so I should stop the recording here. Thank you.